Hello and welcome to the first episode of No Calc. This is an idea I had and finally got out into video form thanks to 3 Blue 1 Brown's video initiative for the summer. And here I will be explaining how you can be able to calculate different things by hand and how you would come up with those methods of calculating things by hand. Today we'll be going over pi. So to start off, I want to explain some expectations for this series. First, I want everything to be able to be natural. How we derive these things, I want them to be something that you could be able to come up with yourself and explain the intuition behind where these methods come from. Second, I want this to be rigorous. Most of this will assume probably a high school background and some calculus. I won't be explaining anything that you learn normally, but anything that pops out and is different, I will be explaining everything involving with that. And third, and most exciting, we'll be doing all the calculations by hand. Wouldn't be no calculation if we didn't do all the hand calculations so that you can see it. One caveat though for this video is we won't be going over the calculation for the square root of 3. We'll be assuming that it's between 1.733 and 1.732. And that's just because I will calculate square roots in more depth in a future video, and we'll prove this later. So let's get started. So first off, when seeing a problem like this, we got to think, what do we actually know? We don't know the value of pi. We're trying to calculate it. And so we don't even know if it's, for instance, 0.01 or 100. So let's try and get some bounds on that. And what I like to do is a method called coming up with the dumbest thing possible. It's a very, very good tool in mathematics if you don't understand something. So let's say we have a circle. We know that the area of a circle with radius 1 is pi. And so we can figure out areas which are maybe bigger or less than the area of the circle. So the dumbest thing I think I could come up with is we can put the circle in a square. Now what's the area of that square? It's not too hard to calculate. We can draw that side. We have 1 as the radius, so the side length is 2. And we immediately get the area is 4 is bigger than pi. In addition, we can come up with another bound on this. For instance, what if we want something smaller? So what if we just cut all these in half? Well, that will be inside our circle, and it'll have half the area of the bigger square, since all of these right triangles are equal. And so we get half of that, or 2 is less than pi is less than 4. So next question is, can we use this idea to be able to come up with a better bound for pi? And those with a geometry knowledge can think of it as, well, what happens if we use a different shape? Probably one of the simplest shapes that we can calculate areas for is a hexagon. Very common in high school geometry. And so if we draw ourselves a hexagon here, we can ask ourselves, what is the area of this hexagon? Regular hexagon. So this will allow us to find a better minimum bound than 2. One way is simply to draw all these lines to the outside. And we have an equilateral triangle of side length 1. And so from geometry, we remember that we can be able to calculate this because this side length is 1/2. This is 1, and then by Pythagoras, this is root 3 over 2. And so the area is 1 times root 3 over 2, which is root 3 over 4. giving the total area of the hexagon 3 square root 3 over 2. There we go. This is less than pi. Now, like I said, we'll be using an approximation for root 3 just to be able to condense this video, make sure it's not too long. So we'll assume that, or well, we won't assume, but we will use the fact that root 3 is between 1.732 and 1.733. So from that, we can get, multiplying both sides by 1.5, 732 times 1.5. And we get 2.59, less than pi. A little bit better. So the next thing we do is to draw a hexagon outside the circle and find the area of that, which will give us an upper bound for pi. So we then have a triangle where the radius to the base is 1 instead. So this gives us 1 over root 3 for that side and 2 over root 3 for this side, which gives us an area of, well, noticing that this is 2 over root 3 and this is 1, the area of this ends up to be root 3 over 3. Multiplying that by 6 for the amount of triangles, we have pi is less than 2 root 3. Then we can use our approximation for root 3 to say pi is less than 2 times 1.733, which gives us pi is less than 3.466. And taking that with our last calculation, we get 2.59 is less than pi is less than 3.47. Now, we can continue this using, instead of a 6-sided polygon, we can instead use a 12-sided polygon. So we draw our circle. And we try a 12-sided polygon inside of it. Now I won't draw the entire 12-sided polygon, but we have this. It's 1/12th section of it. Now we know the angle between this is 30 degrees, and the radius is 1. And it turns out we can actually figure this out using just elementary geometry techniques. Like this. We have a 30, this is 1, which means that this altitude is going to be 1/2 based off of the 30, 60, 90 triangle. And since this is 1, that means the area is 1/4. Multiplying this by 12 actually gives us a very neat bound of 3 less than pi. So finally, we have figured out that pi starts with a 3, which wasn't too bad. In addition, we can figure this out with an upper bound, although it gets a bit messier. I can draw the circle. There we go. So if we draw the outside part of this, we still have this 30-degree angle. However, the distance to this altitude is now 1. So we have to use a bit of trigonometry. find that this angle is 15 degrees. This is 1. Which means that since this angle is this, can be considered the sine over the cosine, we get that this is 1, so that means the cosine is 1, which means that this is the tangent of 15. We can use the half tangent formula to get 1 minus the cosine of 30 over 1 plus the cosine of 30, which gives you, rearranging this around, you get 1 minus root 3 over 2 over 1 plus root 3 over 2, which equals root 2 minus root 3 over 2 plus root 3. Now, using that, we can work with this and simplify it down a bit so that we can calculate it. And this is by multiplying the top and bottom by 2 plus root 3. Actually, by multiplying the top and bottom by 2 minus root 3, we get 2 minus root 3 squared over 2 minus root 3, 2 plus root 3. You can draw. Which gives us 2 minus root 3. This is the difference of squares. 2 squared minus root 3 squared is 4 minus 3, which gives us 1. So, the area of that is 2 minus root 3. Multiplying this by 12, we get 12 times 2 minus root 3 is greater than pi. Then, using our bound of 1.732 is less than root 3, we can substitute that in because it's negative. This will be bigger by substituting a smaller number. We get 2 minus 1.732 times 12. Calculating this out, we get 0.268 times 12, which we can calculate by hand. And we get pi is greater than 3 and is less than 3.22, which is actually a pretty good bound. We're within 0.14 in both directions. Well, 0.15, I guess. You got that little extra bit. Now we'll move on to some of the more advanced techniques in order to figure this out. We have the famous identity pi over 4 is 1 minus 1/3 plus 1/5 minus 1/7, and so on. And there's actually a lot of videos that cover calculating this, and so I won't go too much into it, but the idea is this is actually quite slow. Our original methods are even better than this, but I'll explain how you can actually be able to calculate this rather quickly, and this will lead us to an even better solution, and this is the one I naturally came up with in order to calculate pi to 3 digits. And so what you do is you calculate these fractions, but you make a table of max and min. You just find what the max number is for each of these and the minimum, and you can add them up so that we know which is bigger and which is smaller, so we can only have to calculate the fractions once. So if we want to take this out to say 3 digits, we have 1.000, 1.000, minus 0.333 minus 0.334, since 1/3 is 0.3 repeating. This is the bigger end of that approximation, this is the smaller end, plus 0.200, 1/5 is exactly 0.2, so we don't have to worry about that, minus 1/7, I won't calculate this, specifically, we just have 1, 4, 2, and 1, 4, 3. You can calculate that by hand if you want. And then there's the rest. Now, the thing with the rest of this is it's going to be 1/9 minus 11th plus a 13th minus 15th. This is an alternating series, and so we can actually just add the last one, and this is going to be bigger than everything else, while if we just took everything out, it'll be smaller. The reason is because when we add 1/9, the function goes up. When we subtract an 11th, it goes down, but not quite as much. When we add a 13th, it goes up, and then down, and then up, and then down, and it kind of levels out. So, by adding 1/9, we'll hit the maximum, and by not adding anything, we'll hit the minimum. So, we can have the minimum by just adding nothing, and we can find the maximum by adding 1/9, rounded up, so that we don't go under. And we can add these up. So this gives us 0.837 is greater than pi over 4, less than pi 0.722. Yep. And so multiplying by 4 isn't too hard. We get 2.888 is less than pi is less than 3.21232 348. Now I'm doing a lot of the math in my head, but you can just write it out if that is tricky. And so we have this bound for pi, which we can use with that. We've only considered 4 terms. Using more terms will get this better, of course, because we had to add 1/9. However, even our approximation geometrically is better than this. Now, the question is, how would you be able to find a better way to do this? Well, one way is to just think about where this is coming from. Pi over 4 equals 1 minus 1/3 plus 1/5, and so on. This is a special case of a famous Taylor series identity with the arctangent of x when x is 1. Now, for those of you who haven't seen this before or aren't super familiar with calculus, essentially it comes from this fraction here, 1 plus 1 plus x squared, for values of x less than 1. And we can write this out as an infinite geometric series with multiplicative term x squared. And we get something like this. Integrating both sides, taking the integral of both sides, will be equivalent. And for those of you that aren't familiar with calculus, essentially what we're doing is just changing one function into another function in a special way, which we're allowed to do to both sides. And so we get x minus x cubed over 3 plus x to the 5th over 5, and so on. And you can see that when x is 1, this lines up with this. Now the thing that's special about this is we actually have kind of a geometric series going on with these exponents. And when we stick in 1, it removes this. A geometric series goes down to 0 very quickly, especially very quickly if we have something less than 1 here. Now here, this is going up by odd numbers each time, which is linear. 2n plus 1. This, if we do it right, can be even better than x to the 2n times 2n plus 1. which is exponentially growing. So the question is finding a convenient value for x. Now, pretty much we just want a value between 0 and 1 that we can stick in here and find the value for inverse tangent really quickly. From our trig tables, there's really only one that we can use, and that is the arctangent of 1 over root 3, which comes from pi over 6. So we get this is 1 over root 3 minus 1 over root 3 cubed over 3 plus 1 over root 3 to the 5th over 5, and so on. Now we can rearrange this a little bit by multiplying by the square root of 3, and we get root 3 pi over 6, which can be rearranged to pi over 2 root 3, which is just easier to calculate. And this is 1 minus 1 over root 3 squared over 3 plus 1 over root 3 to the 4th over 5, and so on, which can be manipulated by just squaring this as 1/3, putting it in the denominator. Okay, that works really nice. This is not next. And from here we can just calculate. Now these are fractions just like before. We get 1 minus 1/9 plus 1/45, 3 squared times 5, minus 3 cubed times 7, which is 27 times 7, 9, 4, 29, plus 1 over 9 times 81, and so on. So let's do just like before. We can calculate the max and min. We run into 1/45. We can get this one with long division. Two goes 45. Yeah, all that kind of stuff. And this repeats, so actually we can just repeat this. This should be an upper bound. So you use a 3. 1/89th. Now for this one, we kind of just have to make a guess of 5. And 5 times 189 is 945. That gives us 0.005. Then here, tripling it will give us 54, 567, so that's not going to work. So 2 will, though. This is going to be a lot lower. So our number is going to start with 0.0052. And our last one is, let me clear up some of this. One over 729, 0, 0, 0, 729. This gives us 271 on top. I should not, wait, put that down. This gives us 1 on top, 271 down here. Place that 0. multiplying this by 4 is going to be 2800 something or more, 2900, but that's too much. So 3 should work just fine. 0.0013. So this rounds up to 0.0014, and this rounds down to 0.0013. Now the remaining terms, like I said before, it's going up and down, plus minus, and the terms are getting smaller. So we can just, since the next one's negative, we can just lop everything off to get a maximum, or we can look at the next term and add it, or subtract it rather, to get this one. Now the next term is 1 over 11 times 81 times 3 is 243. Actually times 3, 243. And so this ends up being bigger than 1 over 2000. So we can just say 1 over 2000, which is 0.005. We can do this. This is 0.9074. Doing the other side, which I'll do quick skip through pretty quickly so you can watch it. Gives us 0.9065, which is a really close approximation. It is nice. 65 and 74. Now we can multiply by 2 root 3. Using our bounds before of root 3 between 1.734, 1.732. This gives us 3.464 and 3.466. So we can multiply the small bounds together and the big bounds together. Now this is where computing by hand becomes a lot of computing by hand. This is a 4-digit multiplication, which isn't super bad. I will be doing it just for completeness, but I will definitely be scrolling through this really fast. So bear with me, in a few seconds we'll get this done. And we barely scrape 3.14 being less than pi. On the other end, zooming through the rest of it real quickly. And on the upper bound, we get 3.146. And there we go. We have proved rigorously, other than root 3, that pi starts with the digits 3.14. Using steps that pretty much anybody with a knowledge of calculus, maybe calculus 2, could be able to determine why this works for themselves and possibly even come up with it. So that's it for this video. So glad you were able to watch it, especially those that stuck out all the way to the end, where we were able to get pi equals 3.14. I'm excited to be able to start these, make some more videos, and I am excited to be able to see what kinds of questions you come up with, and please let me know, put in the comments below, different ideas that you have of how to calculate pi. Maybe I'm completely missing something even nicer. Maybe you have your favorite historical calculations for pi. Maybe you've seen some good videos. Just put down any information for how you've found to calculate this and any video ideas that you'd like to see. Thank you so much and take care.